Hello and welcome to our presentation for our IDS 576 project, that's deep learning for portfolio management. And the motivation behind this project is to perform portfolio management using deep learning algorithms. So portfolio management is a decision making process of continuously relocating an amount of fund into several different financial investment products. So this is a resource allocation problem that's continuous in nature, and our aim is to minimize the risk and maximize our returns by implementing deep learning that is very efficient in finding inbuilt patterns, as we have seen that it's very efficient in finding patterns in images and videos and audios. So our goal for this project is to implement a CNN, that is a convolution neural network, for managing a portfolio for various stocks given their past performance. So we have the historical data for the stocks, and we want to maximize our returns by minimizing our risk and by finding relevant patterns in the past data. So we will use the past 31 data of stock history. It outputs a vector of portfolio weights. So this is the primary crux of our model, is to create a vector of portfolio weights that will allow us to figure out how much weights should be assigned to different stocks in our portfolios. So a brief introduction about our data set. It's S&P 500 stock data, that's Standard and Poor's index that has the top 500 stocks that are traded, and the metadata for this data is that it has the date, the name of the stock, for example Google, Amazon, the volume, that be the number of stocks sold and bought on that date, the open would be the dollar amount of that stock with which it opened on the specific day, the high would be the highest dollar amount that it achieved, low would be the lowest dollar amount that was achieved on that day, and the close would be the final closing price. So in this case there's a correlation between the closing price and the open price, as it will a closing price of one day would affect the open price of the next day. So to select our data, we created two new variables. That was the average stock price, that it's a mean of high and low of a stock on that day, and then we calculated the average dollar value traded by multiplying it with volume. So volume is necessary in this case because higher the volume, lower the risk, because it reduces variability in the market. So higher the volume is, there's a good chance if a stock it's being traded more than the other stock, then the inherent risk in that stock is lower because its volume is higher. So we selected top 10 stocks in order of descending dollar value traded. So the methodology for our project is that we implemented a main unit, that be the ensemble of identical evaluators. These are independent evaluators, so each of these look at an individual stock's history and then decide a suitable predicted score for it. These scores from all the 10 evaluators are then input into a softmax function to give the final weight vector for the 10 stocks, and then we implemented this evaluator using a CNN, that is a convolution neural network. So the input for this model was the close, high, low values from our data, and these would be the top 10 stocks that were selected by dollar volume traded in the S&P 500 data set. So batch size for this model was 7 samples, and the window size was 31 previous days. So a little bit about the topology of the model. With our current parameters, 7 is the batch size. There are 10 stocks. We look at the past 31-day history for each stock, and we look at 3 features, that's close, high, and low within our data. After passing these values through 3 convolution layers and a softmax function, we finally get the desired weight vectors. So a little bit about the code organization of our model. The slide details the four main classes we used to create our project. Data class handled the S&P data, and the other three classes handled the training of the trader agent. So the first one, as we said, was the data class that selects top 10 stocks from the original dataset, and it contains a helper function to return batches for training and testing purpose. The second was a trader class that is the main class, which calls other classes. This is responsible for training the CNN and logging the results. Third one is the NN agent class, and it contains the financial formula which are logged, example Sharpe ratio, portfolio vector, value, etc. So in this class, if we find any other financial formulas that can benefit us in optimizing our model, we can just add them to this class later, so we don't have to change the trader class and the data classes. We can just add hyperparameters to this class if we found them later, and if there's a new development in the field of portfolio management. And the last one is the EIIE class, and that contains the actual CNN implemented in TensorFlow. So these are the final results, or the pictorial representation of our result. The first model output or output is the portfolio value. So as you can see that this increases with the number of iterations. So the number of iterations, these are in hundreds. So for 50,000 iterations, you can see a considerable increase in the portfolio value in both the training and the test data sets. The test data sets follows the training data sets pattern very closely. That is, it increases with the number of iterations. The second output of our model was the Sharpe ratio, and the Sharpe ratio is nothing it's but the return that's been adjusted to the risk. So it calculates the risk that was present in the portfolio investment, and it normalizes the return with respect to that risk. And we can also see that the number of iterations at the end, it keeps on increasing, and the test data, it follows the pattern of the training data in that case as well. And it's clear as we approach the higher number of iterations, the model became more and more efficient. And the last output from our model is it's the log mean portfolio vector. So we want to maximize this because it's the log mean of the portfolio vector, and in this case as well, you can clearly see that the number of iterations, when they kept on increasing, the log mean portfolio vector kept on increasing. That means we were increasing the returns that we were generating from our portfolio, and we didn't find any anomaly in the training and the testing data sets pattern in this case as well. They follow each other's pattern pretty closely. And these are the creative contributions that we encountered during creating this model. The first one is the main benefit of having independent evaluators is that they look at the individual stock history independently without looking at other stocks. And the second factor was the optimization, that was selecting suitable CNN configuration and hyperparameters, for example the number of iterations and batch size. Third one, it's program structure, and that's for creating a modular program that can be easily configured with different assets. As I said, that it's a resource allocation problem that heavily depends on the past values and hidden patterns in the data. So if we find any other assets or any other data set that closely mimics the data set that we use, that is of equities or stocks, we can use this model, and all we have to do is just tune our loss functions that according to the data that we are using it, and we can use this model for different sort of data as well, as long as they are pretty similar in nature. And the last one was data handling, that was selecting top 10 stocks by market value. So as you have noticed, you may have noticed that we only selected 10 stocks. That was only because of time and memory constraints. So we could have run this portfolio management on the entire 500 stocks that were present in S&P 500. So this model, we checked it, and it was able to scale pretty efficiently. So we are confident that we can use n numbers of stocks in this model. And the last insight, an interesting insight that we found in this model, was that it had survivor bias in it. And when we looked it up, so the financial industry, it's very famous for survivor bias. So that means they only consider the positive outcomes and not the negative outcomes. So there is a survivor bias in this model as well. And to reduce that, what we did was we reduced the training size of our model to reduce the survivor bias. So those were the creative contributions in this model and in this project. I hope you found them interesting. Thank you so much. Have a nice day.